Hello, welcome to today's lesson. Today's lesson is going to be a review of graphs of trig functions and inverse trig functions. So for this particular lesson, I'm going to try to zip through it and just give you the highlights. If there's anything that you would like additional review on, you can let me know. First, we're going to begin with a review of graphing trig functions. So here are two basic ones to start. We have sine and we have cosine. Hopefully you know which one is which. This one is sine because the y-intercept is 0, 0. It goes up to the right. This one is cosine, nice even function because it has that symmetry with respect to the y-axis. And it drops down to the right and down to the left. And each one has a period of 2 pi. And each one has a domain of all real numbers and a range of -1 to 1. Now, if you ever forget what these graphs look like, remember how we started them. When we first started learning how to graph trig functions, we used the unit circle. And we actually plotted a lot of points the first time, but then when we realized the critical values all occur at quadrant angles. So all the important stuff happens at quadrant angles, multiples of 90 degrees. So all your intercepts, which are points of inflection, your maxes, your intercepts, and your mins all occur at quadrant angles. So if you know just those points on the unit circle, and you know that these graphs are going to be a hill and then a valley and then a hill and then a valley and just repeat, you can always get these graphs again as long as you know that the x-coordinate is cosine and the y-coordinate is sine on the unit circle. So that's how we graph those. And let's take a look next at tangent. For tangent, you can also get the basic graph if you remember just a few things. So it's not likely that we're going to ask you to graph tangent next year, but you want to be aware that it has asymptotes. It has them at x equals -pi/2 and +pi/2. And since the period of this function is pi, the asymptotes will be pi apart, because for tangent, the asymptotes are one full period apart. The other thing you might want to remember is that it reminds me of x cubed. So it goes through the origin, goes up to the right, down to the left, just like x cubed, except it repeats. It's also an odd function, like x cubed. And again, if you ever forget what the graph looks like, one way to kind of get started, at least know where the asymptotes and the intercepts are, is to use the quadrant angles on the unit circle. The definition of tangent is y over x. So if you go to the angle 0, you can put y over x to get 0. That's an x-intercept. And for pi over 2, if you go to the unit circle, at pi over 2, you'll put y over x, and that's going to be 1 over 0, which is undefined. And wherever tangent is undefined, there will be a vertical asymptote. So big deal to remember, it has asymptotes. They're pi apart. The first pair are -pi/2 and +pi/2. And then we have our secant and cosecant graphs next. Sine and cosine, you're probably going to see quite a bit in calculus. Tangent, not as much. Cosecant and secant, rarely. But one thing that's really important to be aware of about cosecant and secant is that they have asymptotes. Next year when you're in calculus, you want to be aware of where the issues may be in a function. So that's why I keep bringing up the asymptotes, because that's where the function's undefined. That's where the function takes a break. So this piece goes up to the right, approaching that vertical asymptote, and then the graph has to take a break before it begins this piece that comes from below from approaching that vertical asymptote. So for cosecant, since that's the reciprocal of sine, you can always graph it by looking at the points of inflection or the x-intercepts for the basic sine graph. That's where the cosecant graph will be undefined, because where sine is 0, the reciprocal cosecant is undefined. So that's how you know where the asymptotes are. And anywhere where sine has a maximum, cosecant's going to have a U-shaped curve that opens up. Wherever sine has a valley, there's going to be a U-shaped curve that opens down for cosecant approaching those asymptotes. Likewise for secant. And last one here is cotangent. We barely saw cotangent this year. You're barely going to see it next year. But here's what cotangent looks like. It has asymptotes. I didn't even write down for you, but if you want to include in your notes, you can, that the asymptotes and intercepts switch from tangent and cotangent. So good to be aware of, but not likely you're going to see cotangent very often. So a couple of quick problems. The domain of cosine with a vertical stretch of 2 and a horizontal shift right pi over 3. The domain remains all real numbers. And that's something you want to be aware of your sine and cosine graphs. It doesn't matter how you move them, stretch them, shrink them, the domain is all real numbers. We're going to call it in calculus well-behaved, because there's no asymptotes, there's no missing points. The graph is nice and smooth and then just continues with that nice wave pattern of hills and valleys forever. Another thing you might want to be able to do is figure out the range after a transformation. So if we think about our sine graph and just think about the range of sine, the fact that the range of sine is -1 to 1, if we take that entire graph and move it up 4, then the range is going to move all the y values up 4. So moving it up 4 is not going to affect the domain, but moving it up 4 will affect the range. So it's going to move this up 4 to +3 and move this up 4 to 5. So if you graph sine x plus 4, you'll see that the range is 3, 5 because the entire graph is going to move up. I'm not going to draw the final one, but if I draw just the original, that has a range of -1 to 1, you can see that if you move the whole thing up 4, the tops, all the maxes that were at 1 are going to move up to 5, and all the mins were at -1 are going to move up to 3 without even actually doing the graph. And then here's one just to review piecewise functions and also to review your sine and cosine graphs. So this piecewise function is going to use 3 times cosine x for all the x's that are smaller than or equal to 0. And then it's going to use the function x, or if you think y equals x, that might sound more familiar. Y equals x is the line that goes straight through quadrants 1 and 3. And we're going to use that wherever x is greater than 0. So I'm going to start with the line because that's like the easier one for me. So I'm going to think y equals x, and they're not always a line and a trig function. It could be 2 trig functions. It could be a linear and a quadratic. Who knows? But I'm going to think y equals x. That has the point 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, -1, -1, and so on. And we're only going to use that function where x is greater than 0. So what I'm going to do is I'm not going to use that down here. I'm only going to do an open circle here and then going through 1, 1, 2, 2, 3, 3 up to the right. I can put an arrow on that because it does continue in that direction forever. No changes beyond that, just continues with that same slope. So that is using y equals x for anything that's greater than 0. Now for 3 cosine x, I only want to use that where x is less than or equal to 0. But that can be kind of tricky because cosine can be a lot of work to graph. So what I'm going to do is use a pencil, and I'm going to first graph cosine. And the x-axis here is tricky as well because I have included the integers, 1, 2, 3, as well as every half pi. So when you go to graph cosine, you want to make sure that your max is at 0, 1, and you're going to hit an intercept at the next quadrant angle, a min at the next quadrant angle, and so on. And I'm graphing more of this graph than I need to, but I know that I am. I'm doing that on purpose because it's easier for me to just kind of graph the whole thing and then just erase the part that I don't want. So there's cosine. Now we want to do a vertical stretch to 3. So instead of having a y-intercept at 1, the y-intercept is going to be at 3. X-intercept will stay where it is because when you multiply 0 by 3, you still have 0. And the minimum at pi -1 is going to stretch down to pi -3. And the intercept at 3 pi over 2 is going to stay where it is. So this is what the graph of 3 cosine x looks like, just kind of the beginning stages of it. Now that I have it going, I'm going to erase the cosine graph. And some of you don't have to graph cosine at all because you just know what it's going to look like when you stretch out by 3. That's cool. And now I want to keep the part where x is less than or equal to 0. So I'm going to put a closed circle up here at 0, 3. And then I'm going to graph this to the left only. And then after 3 pi over 2 at 2 pi, I'm going to go back up to a maximum. And I'm going to erase all that part over there. Because out here to the left, we're not going to put an arrow. For the linear piece, we can put an arrow here because this continues up in that same direction forever. On the left-hand side, I can't put an arrow there. What we did in class is we just truncated the graph. We just chopped it off at the end. And we don't want to curve it down because that's not what the graph does. The graph doesn't go down forever. It's going to have that hills and valleys forever. And if it bothers you to have an arrow on this side and not this side, then don't put an arrow on this side. All right, so that's a little bit of practice with our trig graphs. Let's now move into the inverse trig functions. For graphing inverse trig functions, Here are the steps that I taught in class. So what we would do, for example, if we wanted to graph inverse sine, we would think of the graph of regular sine because we're really good at that. We're familiar with it. And then what we would do is restrict the domain. So we want to make it one-to-one. Right now, this fails the horizontal line test. So if you tried to find the inverse of that whole thing, if you tried to flip this entire thing over the line y equals x, it wouldn't be a function. It would fail the vertical line test. So that's why we restrict the domain. And if we restrict the domain here to only use this blue piece, this piece is one-to-one. This blue portion of the sine graph passes the horizontal line test, and it covers the entire range. The range for sine is normally from -1 to 1 with brackets. The range for that little piece that's blue is also -1 to 1. So we're going to only look at this part for finding the inverse. So we switch the domain and range because that's a characteristic of inverse functions. Inverse functions are all about switching x and y. Then we're going to reverse the ordered pairs. So for the ordered pairs, instead of -pi/2, -1, we're going to have -1, -pi/2. Here 0, 0 becomes 0, 0, and pi/2, 1 becomes 1 pi/2. And then the final thing was to connect the dots by reversing the concavity. So from left to right, this part is concave up, then concave down. So if the original goes concave up to concave down, then the inverse from left to right must go concave down to concave up. And that's how we sketched the graph. Now for cosine, you're going to try that on the practice today, but let's go ahead and review the graph of tangent and inverse tangent. Okay, so the tangent graph is this orange one here. And the domain, it is not one-to-one. If we were to put a horizontal line in here, it would definitely fail the horizontal line test. All right, hits the graph many, many times. So that blue piece in the middle is the piece we're going to use to find the inverse. So when we go to find the inverse, we want to switch the domain and range. We're going to end up with a domain of all real numbers for the inverse, and a range only goes from -pi/2 to +pi/2. When we go to reverse the ordered pairs, the only ordered pair that we have in terms of quadrant is 0, 0. There's lots of other ordered pairs there. The point pi/4, 1 is on there. The point pi/3, radical 3 is on there. But those are hard to kind of see. So in terms of quadrant angles, the only special point there is 0, 0. It's the y-intercept. It's the point of inflection. If we switch that, we still have 0, 0. And then the asymptotes are going to change for tangent. So instead of x equals -pi/2, we're going to have y equals -pi/2. Instead of this vertical asymptote, we're going to have a horizontal asymptote. So just like all the x's and y's switch, the vertical asymptotes become horizontal asymptotes. And then as far as the concavity, look at tangent from left to right, concave down, then concave up. So its inverse is concave up, then concave down. And also remember who tangent reminds me of. It kind of makes me think of y equals x cubed because it goes up to the right and down to the left through the origin. It is definitely not the same as x cubed because the tangent graph repeats. But if tangent reminds me of x cubed, then shouldn't inverse tangent remind me of the inverse of x cubed, which is cube root of x? So that's how I remember how the tangent, arctangent or inverse tangent looks, because it goes up to the right concave down from the x-intercept, and it goes down to the left concave up from the x-intercept. So if that helps you, you can write that down. We are going to review inverse trig functions. So to evaluating inverse trig functions. So when it comes to evaluating, first thing to remember is when you have cos inverse or arccos, arctan or tan inverse or sine inverse or arcsine, you have angle restrictions. So for arc cosine, the angle restrictions are 0 to pi. And the way that we remember that is we remember what the restrictions were when we found the graph of the inverse. So that right there is regular cosine, not the inverse. It's regular cosine. And when you go to do your practice today, when you go to restrict the domain, you're going to make the domain 0 to pi. So for the restrictions on the inverse trig functions, it's whatever the restricted domain was of the original. It's actually because it becomes the range of the inverse trig function. But you can remember them easily by going back to the original graph. Because for arctangent, think about what the restricted domain was. This blue part had a restricted domain of negative pi over 2 to positive pi over 2. And that's just that blue part there. And then for inverse sine, arc sine, if we go back to the original sine graph, look what the restricted domain was. It was negative pi over 2 to positive pi over 2. That became the range for the inverse. But I think the easier way to remember the angle restrictions, as we called them in class, is to think back to the original and what did you restrict the domain to? Because you know this graph really well. This graph is less familiar to you, but the regular sine graph, you know it very, very well. So the angle restrictions for arc sine are negative pi over 2 to positive pi over 2 with brackets because you do want to include those endpoints, unlike arc tangent where you have to use parentheses because of the asymptotes. So here's how we solved. We said, okay, if we have arc cosine or cosine inverse, this is the ratio, so we're looking for an angle. Arc cosine or cosine inverse makes me uncomfortable, so I'm going to change that to regular cosine. But if I'm going to change that to regular cosine, I have to switch the input-output, because that's what inverses are all about. So all we're trying to do is solve for the angle when cosine is negative 1/2. So using the skills we reviewed in the last Edpuzzle, the last video, we can find the reference angle, which is going to be 60 degrees, which is pi over 3 in radians. And then instead of jumping right into all students take calculus, don't jump right into that. Use your angle restrictions for arc cosine, okay? Because the moment arc cosine's involved, we have to stick between 0 and pi. So if you have to be between 0 and pi, that means quadrant 3 and 4 are off limits. You can only be in quadrant 1 or 2. So if all students take calculus and cosine is negative, we must be in quadrant 2. And the angle in quadrant 2 that has a pi over 3 reference angle is 2 pi over 3. Let's do another one together. For arc tan of negative 1, I first recognize that I'm looking for an angle, because for inverse trig functions, you put in a ratio, get out an angle. Arctan makes me uncomfortable, so I'm going to switch this to regular tangent. So tan theta equals negative 1. Using the skills from the last video, we can figure out that the reference angle is 45 degrees or pi over 4. Unit circle or your triangles, whatever you prefer. And then because arctan was involved, we have to be between negative pi over 2 and positive pi over 2. So don't jump to all students take calculus when you're doing inverse trig functions, because you have to stick within those angle restrictions. So we're not allowed to go past pi over 2. We're not allowed to go past negative pi over 2. So of the two quadrants we can choose from, tangent is negative in quadrant 4. So the angle in quadrant 4 that has a pi over 4 reference angle, we usually call it 7 pi over 4, but you're not allowed to here. You can't call that angle 7 pi over 4, because to draw 7 pi over 4, you had to go past pi over 2. The largest angle you're allowed to have is just smaller than pi over 2 because of those parentheses. You're not allowed to have an angle that's bigger than this. So what we have to do is we have to rename the angle. So instead of calling this angle 7 pi over 4, we find an angle that's coterminal, and this one will do it. Negative pi over 4 is the answer. And when you're evaluating inverse trig functions, remember these are functions. So each input has exactly one output. So you should only get one answer. You should only get one answer for inverse trig functions, and they should always be in radians. Now for the last one, that's evaluating inverse sine. So we can go through the same process, but we'll find that it has to be a quadrant angle because none of the reference angles work. So the angle restrictions for inverse sine were negative pi over 2 to positive pi over 2 with brackets. That means you're off limits over here. You can't be to the left of the y-axis. So there's only 3 quadrant angles in that restricted. It's actually a range for inverse sine. But within the angle restrictions, there are only 3 options. And the one where sine is 0 is right here. You can't call that angle 2 pi. Because 2 pi would be bigger than pi over 2. The largest angle you're allowed to use is pi over 2. But you can call it 0 because 0 is between negative pi over 2 and positive pi over 2. All right. I know that review was quick. This is some pretty intense material. So if you have any questions, be sure to ask them in the Google Doc. and be sure to do the practice. And there's a video to go along with the practice if you would like to watch it.